There are galaxy clusters in our universe moving at over 2 million miles per hour towards something we cannot see. Not moving away from each other, as the Big Bang predicts. Not following the expansion of space itself. Moving together, in formation, toward the same point beyond the observable universe. Every galaxy cluster we can observe, containing billions of stars each, is being pulled by something outside everything we've ever known. Imagine standing on Earth and discovering that our planet, our solar system, our entire galaxy, and hundreds of thousands of neighboring galaxies are all drifting in the same direction like leaves caught in an invisible current. A current that originates from beyond the edge of reality itself. The most sophisticated instruments humanity has ever built have confirmed it. The cosmic microwave background, the afterglow of creation, carries a signature that shouldn't exist. Something is pulling at the very fabric of our universe. What if the universe we see, with its 2 trillion galaxies, its 93 billion light-year span, everything from the beginning of time to the edge of observable space, is not the whole story? What if we are inside something much, much larger? Today, we journey through evidence that challenges everything we thought we knew about the cosmos and our place within it. Prepare yourselves. We begin. In 2008, a team of astronomers led by Alexander Kashlinsky at NASA's Goddard Space Flight Center published findings that would shake the foundations of cosmology. They had been studying the cosmic microwave background radiation, the oldest light in the universe, released just 380,000 years after the Big Bang. This faint glow, cooled over 13.8 billion years to just 2.7 degrees above absolute zero, forms the canvas upon which the entire history of the universe is painted. But something was wrong. Kashlinsky's team had analyzed the motion of over 700 galaxy clusters, the largest gravitationally bound structures in the universe. Each cluster contains hundreds or thousands of galaxies, billions of stars, and incomprehensible amounts of dark matter. These are not small objects drifting aimlessly through space. According to the standard model of cosmology, these clusters should be moving essentially randomly, affected only by local gravitational interactions and the overall expansion of space. Like cities scattered across an expanding balloon, each moving away from all others at predictable rates determined by their distance. What the team discovered was impossible under current theory. The galaxy clusters weren't moving randomly. They were moving coherently, in the same direction, at velocities exceeding 3.2 million kilometers per hour. That's roughly 2 million miles per hour. Fast enough to cross the distance from Earth to the Moon in 7 minutes. More disturbing, this collective motion extended across the entire observable sky. Galaxy clusters separated by billions of light-years, with no causal connection to each other, were somehow moving in concert. They called it the dark flow. Think of it this way. Imagine you're in a swimming pool, watching leaves float on the surface. Local currents push individual leaves in different directions. But now imagine every leaf, from one end of the pool to the other, suddenly begins drifting in the same direction. The current pulling them isn't coming from inside the pool. It's coming from outside. The implications were staggering. In standard cosmology, the observable universe represents a causally connected region of space. The cosmic microwave background radiation we see in all directions traveled from the edge of the observable universe to reach us. Beyond that edge, information cannot reach us. The universe hasn't existed long enough for light to travel from there to here. This boundary should represent an absolute limit on physical influence. Nothing beyond the observable universe should be able to affect anything within it. That's not philosophy. That's the finite speed of light combined with the finite age of the universe. And yet, here was evidence of exactly that. A force originating from beyond the observable universe, powerful enough to drag galaxy clusters, objects with a mass of 1 billion suns, across cosmic distances. The response from the scientific community was immediate and skeptical. Alternative explanations emerged. Perhaps it was systematic error in measuring the cosmic microwave background. Perhaps local gravitational anomalies created the illusion of coherent motion. Perhaps the statistical analysis was flawed. But Kashlinsky's team had been careful. They had used data from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, one of the most precise instruments ever deployed in space. They had corrected for known systematic effects. They had applied rigorous statistical methods. The dark flow didn't make sense. But the data was real. As word spread through the astronomical community, other researchers began examining the evidence. Some found flaws in the methodology. Others confirmed the findings using different techniques. The debate intensified. But here's where the story takes a crucial turn. The dark flow wasn't the only anomaly. In 2013, astronomers using the European Space Agency's Planck satellite, an even more sensitive instrument than WMAP, made another disturbing discovery. The cosmic microwave background radiation, which should be almost perfectly uniform across the sky after accounting for known effects, contained large-scale patterns that violated the cosmological principle. The cosmological principle states that the universe should look essentially the same in all directions when viewed at large enough scales. It's a foundational assumption of modern cosmology, built into Einstein's equations and confirmed by decades of observations. The Planck data revealed a cold spot, a region roughly 1.8 billion light-years across where the cosmic microwave background is significantly cooler than surrounding areas. And it wasn't alone. The data revealed asymmetries across the entire sky, patterns that suggested the universe had a preferred direction. The same direction as the dark flow. But the evidence forces us to confront an uncomfortable possibility. What if our universe, vast as it is, exists within something even larger? What if the dark flow represents the gravitational influence of structures beyond our cosmic horizon? What if we are not alone in the multiverse? Let me be clear about what we're discussing. The dark flow is not a minor statistical fluctuation. It represents a bulk motion of matter on the largest scales observable in the universe, moving at velocities that challenge our understanding of cosmic structure formation. In 2010, Harold Ebeling at the University of Hawaii and his colleagues analyzed X-ray data from NASA's Chandra X-ray Observatory, examining over 800 galaxy clusters. X-ray observations provide an independent measure of cluster motion by detecting the hot gas that fills these cosmic structures, gas heated to tens of millions of degrees. They confirmed it. The galaxy clusters were moving coherently toward a region in the southern sky, in the direction of the constellations Centaurus and Hydra. The velocity, approximately 1,000 kilometers per second, or 2.2 million miles per hour. For perspective, our entire Milky Way galaxy orbits within the local group at about 100 kilometers per second. The dark flow represents motion 10 times faster, affecting structures millions of times more massive. Scientists discovered another signature in the polarization patterns of the cosmic microwave background. When photons scatter off electrons in the early universe, they become polarized. Their electromagnetic waves oscillate in preferred directions. These polarization patterns encode information about the motion and distribution of matter in the infant cosmos. Fernando Atrio Barandella at the University of Salamanca analyzed this polarization data and found something remarkable. The patterns showed systematic distortions consistent with large-scale bulk flow extending across gigaparsecs, billions of light-years, of space. The probability of this occurring randomly in a universe governed by standard cosmological models? Less than 1 in 10,000. Here's what makes this particularly compelling. These are completely independent measurements. The X-ray data, the cosmic microwave background temperature, and the polarization data all come from different physical processes, detected by different instruments, analyzed by different teams. And they all point to the same conclusion. But conventional explanations struggled to account for the observations. Some astronomers proposed that nearby superclusters of galaxies, like the Shapley concentration, containing more than 8,000 galaxies at a distance of 650 million light-years, could generate the required gravitational pull. The numbers didn't work. The Shapley supercluster, massive as it is, contains roughly 10 quadrillion solar masses of matter. That's a 10 with 16 zeros. But calculations showed this wasn't nearly enough mass to produce the observed velocities across such vast distances. You would need structures hundreds of times more massive, extending far beyond what we can observe. Other researchers suggested that perhaps dark energy, the mysterious force causing the universe's expansion to accelerate, had properties we didn't understand. Perhaps local variations in dark energy density could create the apparent motion. But dark energy pushes things apart. The dark flow represents matter being pulled together, moving toward a common point. The physics doesn't align. Then came the theoretical work. Michael Merrifield at the University of Nottingham and his collaborators ran sophisticated computer simulations of cosmic structure formation. They generated thousands of model universes, each with different initial conditions and physical parameters, all constrained by observations of the cosmic microwave background. In none of these simulated universes did bulk flows comparable to the dark flow emerge naturally from the evolution of structure within a finite, isolated universe. To reproduce the observations, they had to introduce external influences. Gravitational effects from beyond the observable universe. Structures existing in regions of space from which light has not yet had time to reach us. But this represents just one piece of a much larger puzzle hidden in the fundamental structure of reality itself. The evidence extends beyond peculiar motions into the realm of cosmic topology, the shape and structure of the universe itself. In 2014, a team led by Rainer Kuck at the University of Bielefeld analyzed data from the Planck satellite and discovered what they called the axis of evil, an alignment of features in the cosmic microwave background along a preferred axis in the sky. This shouldn't exist. The cosmic microwave background should be statistically isotropic, the same in all directions, aside from small random fluctuations and the known dipole pattern caused by Earth's motion through space. The axis of evil represented something different. Large-scale structure in the pattern of temperature fluctuations that implied the universe has a preferred orientation. The alignment pointed in the same direction as the dark flow. Consider what we're really observing. The cosmic microwave background radiation we detect today was emitted when the universe was just 380,000 years old, less than 0.003% of its current age. The photons we measure have been traveling through space for 13.8 billion years before reaching our detectors. Any pattern in this radiation reflects conditions in the early universe. If the cosmic microwave background shows large-scale asymmetries, it means the universe itself was asymmetric at birth. Not just locally, but across the entire region of space we can observe. Standard inflationary cosmology, the theory describing the universe's first fraction of a second, predicts that any initial asymmetries should have been stretched and diluted to undetectable levels. The observable universe should have emerged from inflation statistically homogeneous and isotropic. The data suggests otherwise. The most remarkable discovery involves what cosmologists call the CMB anomalies, a collection of unexpected features in the cosmic microwave background that, taken together, paint a disturbing picture. First, the low quadrupole and octupole moments. These mathematical terms describe large-scale patterns in the temperature map. They're significantly weaker than predicted by standard cosmology, as if something suppressed structure formation on the largest scales. Second, the hemispheric asymmetry. The northern and southern halves of the sky show systematically different properties in their temperature fluctuations. One hemisphere appears slightly warmer, with larger fluctuations, than the other. Third, the cold spot I mentioned earlier, a region 1.8 billion light-years across that's roughly 70 microkelvins colder than its surroundings. Several theories have attempted to explain it: a supervoid along our line of sight, a statistical fluke, or even a collision between our universe and another. Laura Mersini-Houghton at the University of North Carolina proposed an audacious explanation. She argued that these anomalies represent the gravitational influence of other universes in the multiverse, bubbles of spacetime that formed during the same inflationary epoch that created our own universe. According to her calculations, if our universe nucleated near other bubble universes during inflation, their gravitational effects would have left an imprint on our cosmic microwave background. This imprint would appear as large-scale asymmetries and preferred directions. The direction of maximum gravitational influence toward the cosmic regions showing the dark flow. This is where the evidence becomes almost impossible to ignore. We have independent observations of bulk flow, cosmic microwave background asymmetries, anomalous large-scale structure, and theoretical predictions from multiverse models, all pointing toward the existence of influences from beyond our observable universe. Critics rightfully point out that extraordinary claims require extraordinary evidence. Some astronomers still argue that the dark flow could be a systematic error, that better analysis of the data will reveal conventional explanations. But with each new observation, with each independent confirmation, the conventional explanations become increasingly strained. The evidence extends beyond mere motion into the fundamental properties of spacetime, suggesting that what we call the universe might be just one finite region within a vastly larger cosmos. To understand what the dark flow might represent, we need to examine the theoretical framework that could accommodate it: the multiverse. The concept didn't originate with the dark flow. It emerged from several independent lines of theoretical physics, each pointing toward the same unsettling conclusion, that our universe is not unique. Inflationary cosmology, developed by Alan Guth in 1980 and refined by André Linde, Paul Steinhardt, and others, describes the universe's first moments. According to this theory, the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang, growing from subatomic scales to cosmic dimensions in less time than it takes light to cross a proton. But here's the crucial insight: once inflation starts, it may never completely stop everywhere at once. Imagine a pot of boiling water. Bubbles form continuously, each representing a region where the water transitions from liquid to gas. In eternal inflation theory, our universe is like one of those bubbles, a region where inflation ended and normal expansion began, surrounded by an eternally inflating space where new bubble universes continuously form. André Linde calls this chaotic inflation. In his model, the inflaton field, the quantum field driving inflation, has different values in different regions of space. Where the field reaches certain values, inflation ends and a universe forms. Where it remains high, inflation continues, spawning new regions that will eventually become universes of their own. The multiverse that emerges from eternal inflation is staggeringly vast. Our observable universe, 93 billion light-years across, would be an infinitesimally small patch within a single bubble universe, which itself would be one among countless bubbles in an infinite inflating space. Now ask yourself, what happens at the boundary between bubbles? This forces us to reconsider fundamental assumptions about cosmic isolation. If our universe exists within a multiverse landscape, and if other bubble universes nucleated nearby in the same inflating space, their gravitational influence doesn't simply disappear. Gravity, unlike light, may propagate through the higher dimensional space, the bulk that contains the bubble universes. This is a key prediction of string theory and brane cosmology, where our universe might be a three-dimensional membrane floating in a higher dimensional space. If this is correct, then massive structures in neighboring universes could exert gravitational pull on matter in our own universe. We couldn't see these external structures, their light hasn't reached us and may never reach us. But their gravity would affect us nonetheless. The dark flow could be exactly this: the gravitational signature of vast cosmic structures existing in adjacent regions of the multiverse, pulling on galaxy clusters in our observable universe. Anthony Aguirre at the University of California, Santa Cruz, and Matthew Johnson at York University have developed detailed models of bubble universe collisions. Their calculations show that if our universe collided with another bubble universe early in cosmic history, it would leave distinctive imprints, asymmetries in the cosmic microwave background, preferred directions, and potentially large-scale bulk flows. The patterns they predict match the observations remarkably well. But competing interpretations exist. Some cosmologists argue that the dark flow, if real, could represent quantum fluctuations from the inflationary era, random variations that by chance created large-scale structure extending beyond our observable horizon. Given infinite space and infinite time during eternal inflation, even incredibly improbable configurations must occur somewhere. Others suggest modifications to general relativity itself. Perhaps gravity behaves differently on the largest scales than Einstein's equations predict. Perhaps dark matter has properties we haven't discovered. Perhaps dark energy varies in density across cosmic distances, creating apparent bulk flows. These alternatives remain possibilities, but they lack the explanatory power of the multiverse hypothesis, which naturally accounts for multiple independent observations within a single theoretical framework. The scientific investigation of the dark flow continues with increasingly sophisticated tools. The European Space Agency's Euclid mission, launched in 2023, is mapping the three-dimensional distribution of galaxies across a third of the sky, measuring the shapes and positions of billions of galaxies with unprecedented precision. This data will allow astronomers to test whether large-scale bulk flows exist and, if so, to measure their properties with far greater accuracy than previous studies. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will conduct even deeper surveys, probing the structure and evolution of the universe across cosmic time. Its wide-field infrared observations will trace the motion of galaxy clusters and detect subtle distortions in the cosmic web caused by massive structures, whether in our universe or beyond it. Recent breakthroughs suggest we may soon have direct observational tests of the multiverse hypothesis. Gravitational wave astronomy has opened an entirely new window on the cosmos. The LIGO, Virgo, and Cagra detectors have observed dozens of black hole and neutron star mergers, detecting ripples in spacetime itself. Future gravitational wave observatories, including the space-based LISA mission and next-generation ground-based detectors, will be sensitive enough to detect gravitational waves from the earliest moments of cosmic history. If our universe collided with another bubble universe, or if we exist near other bubble universes in the multiverse, these events would have generated gravitational waves, a primordial background of space-time ripples that should still be detectable today. The pattern of this gravitational wave background would encode information about the geometry and topology of the multiverse itself. We could, in principle, map the landscape of bubble universes surrounding our own. Avi Loeb at Harvard University has proposed another test, looking for symmetry breaking in the fundamental forces. If our universe formed through a phase transition as a bubble nucleated in the inflating space, and if neighboring bubbles nucleated nearby, the collision or proximity of these bubbles could have broken symmetries in unexpected ways. This might manifest as variations in the fine structure constant, a dimensionless number describing the strength of electromagnetic interactions across the sky. Current measurements show no such variation, but future instruments may be sensitive enough to detect the tiny effects predicted by multiverse models. The implications extend into particle physics. The Large Hadron Collider at CERN has not yet discovered physics beyond the Standard Model. No supersymmetry, no extra dimensions, no new fundamental particles except the Higgs boson. This nightmare scenario has puzzled physicists who expected new physics to emerge at the energy scales the LHC can probe. But in a multiverse where different bubble universes have different physical constants and particle physics properties, our universe might simply exist in a region of the landscape where new physics lies beyond our reach. The energy required to probe extra dimensions or detect supersymmetric particles might be higher than any conceivable accelerator could achieve. This doesn't mean we can't test these ideas. It means we need different approaches, precision measurements of known particles, searches for rare processes, and most importantly, cosmological observations that can reveal the structure of the multiverse indirectly. What this means for us, for humanity, is profound. If the dark flow is real, if we truly detect the gravitational influence of structures beyond our observable universe, it would represent the first empirical evidence that we inhabit a multiverse. Not philosophical speculation. Not mathematical possibility. Observable, measurable, testable evidence that reality extends far beyond the cosmic horizon we can see. The implications for our understanding of existence itself would be revolutionary. The most profound implications emerge when we consider what the multiverse means for the nature of physical law. In our universe, the fundamental constants of nature, the strength of gravity, the charge of the electron, the mass of the Higgs boson, have very specific values. Change any of these constants by even a small percentage, and atoms couldn't form, stars couldn't shine, and life as we know it couldn't exist. This fine-tuning has puzzled physicists for decades. Why do the constants have precisely the values needed for complexity and life? Some argue for an intelligent designer. Others invoke the weak anthropic principle. We observe these values because only in a universe with these values could observers exist to make the observation. But the multiverse offers a different perspective. If eternal inflation creates a vast ensemble of bubble universes, and if the physical constants vary from universe to universe, taking different values in different bubbles, then our existence in a life-friendly universe requires no explanation beyond probability. With infinite universes exploring all possible combinations of constants, some will inevitably have the right conditions for life. We find ourselves in one of those universes not because it was designed for us, but because only in such universes could beings capable of asking the question exist. This is not a trivial philosophical point. It's a testable hypothesis with specific predictions. If our universe's constants are selected purely by anthropic reasoning, existing only because they permit observers, then we should find ourselves in a universe where the constants are barely sufficient for life, not far more life-friendly than necessary. And remarkably, this appears to be the case. Detailed calculations show that small changes to most fundamental constants would make the universe uninhabitable. We live right at the edge of the parameter space that allows complex chemistry and stable stars. But here's where it gets strange. If the dark flow reveals the existence of other bubble universes, those universes might have wildly different physical laws. Not just different constants, but different numbers of spatial dimensions, different forces, perhaps even different mathematical structures governing reality. String theory predicts roughly 10 to the power of 500 possible vacuum states, different configurations of the extra dimensions, each corresponding to a different set of physical laws. If even a tiny fraction of these possibilities are realized in the multiverse landscape, the diversity of universes would be unimaginable. Some universes might be simple, containing only radiation and no matter. Others might be so complex that they collapse into black holes immediately after forming. Some might evolve for trillions of years, developing structures we cannot conceive. The most disturbing evidence comes from considering time itself. If eternal inflation is correct, then the multiverse has no beginning and no end in any conventional sense. New universes constantly nucleate, existing within an ever-inflating space. The arrow of time, so fundamental to our experience, might be a local property of our bubble, not a universal feature of reality. This raises questions that seem almost absurd but follow logically from the evidence. If the multiverse is infinite, containing every possible universe, does that mean all possible histories occur? Do universes exist where physical constants varied over time? Where the laws of physics are different in different regions? Max Tegmark at MIT has proposed a hierarchy of multiverse levels, with eternal inflation representing just level 2. Different universes with different physical constants but the same fundamental mathematical structure. He argues that level 4 would include all possible mathematical structures, all possible ways of organizing information and causation. If he's right, then reality is far stranger than even the wildest science fiction imagines. Every consistent mathematical structure, every way of combining logic and rules, would exist as its own form of universe, its own instantiation of reality. The dark flow would represent our first glimpse beyond the boundaries of our own mathematical structure, detecting the gravitational shadow of universes fundamentally unlike our own. And yet, amid this bewildering cosmic landscape, one fact remains: we exist. We observe. We measure. We calculate. Against the infinite backdrop of the multiverse, on one small planet in one ordinary galaxy in one unremarkable region of one bubble universe, conscious beings emerged who can contemplate their own place in existence. The dark flow, if it's real, tells us that our cosmic address is far more complex than we imagined. We're not just on Earth, in the solar system, in the Milky Way, in the local group, in the Laniakea supercluster, in the observable universe. We're in one bubble among countless bubbles, drifting through an eternal inflation that may have no end, part of a multiverse whose true scale and structure we're only beginning to glimpse. So where does the evidence leave us? The dark flow, if it survives continued scrutiny, represents something unprecedented in the history of astronomy. Not just the discovery of a new object or a new phenomenon, but the first observational evidence that reality extends beyond everything we can ever hope to see. The cosmic microwave background anomalies aren't just statistical flukes. They encode information about the initial conditions of our universe, information that suggests we emerged from a larger multiverse landscape. The theoretical framework isn't just mathematical speculation. It's the natural consequence of our best theories of cosmic origins, pointing toward a reality far grander than the observable universe. We've learned that our universe, vast as it is, may be a finite bubble within an infinite inflating space. That the physical laws we observe might be local accidents, selected from countless possibilities. That the very concept of the universe needs revision. We live not in the universe, but in a universe. Yet profound mysteries remain. We don't know if the dark flow interpretation is correct. We don't know if we'll ever develop technology capable of directly observing other bubble universes. We don't know whether the multiverse is finite or infinite, structured or chaotic, comprehensible or beyond all understanding. The current scientific consensus is cautious. Most cosmologists acknowledge the evidence for anomalous large-scale structure and bulk flows, but debate their interpretation. The multiverse remains a hypothesis, not an established fact. More data is needed. Better analysis is required. Alternative explanations must be explored. But the journey continues. And perhaps that's the most important lesson. 100 years ago, we thought the Milky Way was the entire universe. 50 years ago, we didn't know about dark energy or cosmic inflation. 20 years ago, the multiverse was pure speculation with no observational hooks. Today, we have the dark flow, a whisper from beyond the edge of everything, suggesting that reality is stranger and more magnificent than our ancestors could have dreamed. The universe is vast. The multiverse might be infinite. The mysteries are endless. But we're here, asking questions, building instruments, analyzing data, pushing against the boundaries of knowledge. And somewhere out there, beyond the cosmic horizon, beyond the limits of light and time, the greater cosmos awaits our discovery. The journey continues.